Okay, for our final remote learning lesson, this should be a quick video. So first thing I want you to do is just have a go at this, finding the area of the region bounded by the graph y equals log x, the line x equals 2 on the x-axis, and try and do that by hand. There is a way to do it, but you'll have to think back to the very beginning of integration and a little example that we looked at and then haven't looked at since. Have a go, and then we'll talk about it in a second. Okay, so in order to complete this integration by hand, we actually have to find an indirect way of finding the area because we don't have an antiderivative of log x. We don't have something which just neatly differentiates to give us log x, and so integrating with respect to x isn't an option. But if you were able to think back to an example we did really early on, what we can do is invert the function. We can represent it as x equals e to the power y, and then what we can do is integrate with respect to y, find the area between the curve and the y-axis, and then subtract that from the little rectangle that's formed. So really well done if you did that. But the focus of today's lesson is on ways in which we can use our CAS calculator to support us when we get problems that we can't solve by hand. And so, over to our notes. What we're going to look at is just 4 cases of how to do that. And I'm not going to go through using the calculator in detail for each of them. I think it'll be a bit clumsy and time consuming. I posted some links to some websites that just help you with some tutorials if you're not so confident with this. But what I want to focus on as we talk about it is the 4 different cases. So the first one is kind of what we just spoke about with that example. We've got the integral of y equals log x, and we don't have a simple analytical form for that. And so we can try something like inverting the function, like we just spoke about, or we can go to our technology and we can ask for support. And so if we find something that we don't know how to integrate by hand, our calculator can help us with it. We find the integral function under interactive calculation, or you can actually find it on your keyboard, but you've got to choose the definite option, and then you can put in your limits, and away you go. The second way in which you can use your CAS is to find the signed area if or to find the total area, I should say, if you don't know an intercept. So here we've got this function y equals e to the power sine x minus 2, and we're trying to find the total area of the shaded region here. So this isn't about the signed area. We're trying to find the total area, and so what we need to be able to do is identify this point A, and solving that analytically is not impossible, but it's clumsy, right? You'd have to set y equal to 0, and we'd have to find the correct root, the correct value of A. Our CAS can help us here because what we can do is we can find that root using solve, remembering to restrict the domain of the functions between pi over 2 and 3 pi over 2, so it gives us the right root. Then when we've got that root, we can put that in to the calculator to work out the area on the left and the area on the right and add them up. So 2 ways to find to find the calculator useful. We're going to look at 2 more. And these are a little bit different. So if you remember, the fundamental theorem of calculus states that the integral of a function f of x between a and b is the same as the antiderivative at b subtract the antiderivative at a. And what we're going to do is we're just going to change up our notation a little bit. I'm going to use x1 and x0 instead of a and b. That's neither here nor there. But what I'm also going to do is just rearrange it so I make one of the endpoints the subjects. So rearranging this, f of x1, which is going to be my b, equals f of x0, the f of a, plus the integral from x0 to x1 of f of x dx. What this allows us to do is to evaluate the antiderivative at a given point if we know what its value at another point and we know the behavior of the gradient. So for example, here's an exam question. If we know the gradient is defined by this function, and we know that y has a certain value at x equals 0, it asks us to find the value of y when x equals 4. Now we could do this by hand, and there'd be, we would integrate, we'd find the function, we'd work out the value of c, etc. But, perhaps an alternative way, and another tool for our toolbox, is to use this method. So what we're saying here is that the function y equals big F of x, right? This is the antiderivative where dy by dx is little f of x. And so big F of 4 equals big F of 1 plus the integral of 2x to the power 6 plus 1 to the power half dx. Put this into our CAS, give us our answer. Happy days. Okay. Final example of a way in which we can use these calculators. And this is actually to build on that idea and that rearranging of the fundamental theorem of calculus, but actually to use it to define a function in quite a sneaky way. And this is probably the newest thing and the thing that will require the most getting used to that we look at today. So what I'm going to do is I'm going to take the formula, the rearranged form of the fundamental theorem of calculus, and I'm going to swap out my x0 for a and my x1 for x. And they're just symbols, so there's no problem at all with doing that. And because I'm using my x now as one of the limits, I can't use it in my integral as well, but so I'm going to introduce a dummy variable t. And we can call it a dummy variable because it's there, but it's going to disappear. We evaluate the integral, and then we're going to substitute in a and x. So that dummy variable t isn't going to appear in our final expression. Now, this is kind of powerful because x is our general variable here, and we've done something kind of subtle because we've taken what was a constant and we've replaced it by a variable here to actually define the function. I'm just going to simplify it ever so slightly just by noting that we know that any function would have an infinite amount of antiderivatives, and we know that f of a here is just a constant. So we could say, if I do this here, because f of a is a constant, g of x, which is just equal to the second part here, the antiderivative part, is also an antiderivative of f of x. So there's two ideas here. The second one, the thing I just did in green, that's kind of basic. What we're doing here is we're just going, oh, well, this is a constant, So that's like your plus c for your antiderivative. So we can just forget about that, and we can just say that this function without the constant is another antiderivative. Apart from that, this here on the right hand side is a pretty roundabout way to define a function in terms of x. And what we're saying here is you've got your start point, and we've got the gradient function, and what you're going to do is you're going to integrate up until the value of x. And so it's kind of like a moving area. As you increase x, the area is going to increase, and the area at any point in time is going to be given by the integral g of x. Now, here's an example, and they've defined a function. And if you look at the language here, this is kind of what I want you to understand, that this is a legitimate way of defining a function in terms of x. We have a dummy variable t, and we have our actual variable x being the upper limit of the integral. And what happens as x increases is we get this moving area. So we get the moving area as x increases, and that helps us define the function. So on your CAS calculators, if you can define a function in this way, you can just drag it onto the graph, and it will plot it for you. And that's really the skill you're going to look at. In the second example here, you define a function that way, using the variable as the upper limit, and then you drag it onto the axes, and it will plot that antiderivative for you, and you can analyze it using all the normal methods. So that's enough for me today. Have a go at this, and we'll pick up when we're in school next week. See you really soon.